Okay, you just read about linear regression. Let's go ahead and start building a linear regression, a multiple linear regression with our insurance data here. So you can see here I've got my insurance data, and in order to make it easier to run multiple linear regression in Excel, the first thing I want to do is I want to organize my columns so that all my numeric columns are together. So I'm going to start off by just adding a new column here. And I will bring over children into this column here, and then I'll get rid of the column B. Okay, so now I can run a regression. Let's go ahead and give that a try. If I go to data and data analysis, I can bring up my regression tool here. And we start by defining what our Y value is, and that's our charges. All right. And then it says, well, what are our X values? And remember, in multiple linear regression, we can have multiple X values, which is what we have here. So we will highlight all three of these, top to bottom. So G1 to G1339, D1 through F1339. I do want to let the regression tool know that this does have labels. And we can leave that confidence level at 0.95, that's fine. And then if yours defaults to a new worksheet, we can change that. We'll just make our output range, and I would stick it over here a little bit to the right of everything so we have a little bit of room to do some analysis. So I'm going to go ahead and just stick it right here. Let's make it in whoops, I'm way down at the bottom. So I want to come back up to the top and make sure I'll start in 05. All right. Now there are options to show what the actual residuals are and standardized and put some graphical plots out there. You're welcome to do that and see what the results are. We don't need to do that for what we're trying to accomplish here. So we'll just click OK and we get our output. So we now have, and I'm just going to format this to make it a little bit easier on the eyes. All right, so now I'll resize my columns. All right, so what do we have here? Well, the first thing we might notice is we have an R-squared value up here of 0.12010. And you might recall R-squared is one of the measures we use to determine how well the regression model fits our data. How much does it explain our data? It's the percent accuracy of our model. Well, that's not exactly true. What it does is it explains about 12% of the variation, the variance in our charges based on the model we've put together here. Another factor down here is the adjusted R-square. And that's an important one to consider because the R-squared is going to continue to increase no matter how many additional variables we add. The adjusted R-squared is a good one because it actually starts to tell you when your model is not really gaining anything by adding new variables. It will actually start to go down. So the adjusted R-squared is a good one to keep an eye on as you're building these models as well. But the R-squared is our primary measure of performance for the model. We'll take a look at a couple others in just a minute, but first let's see what we have here. So the first thing we have is our F-score for the overall model. So you can see that the regression actually runs at ANOVA for us. And the F-score is 6.09 or 6.069. So that's a pretty good F score. And you can see that the significance of F, let me highlight that. The significance of F is also what? 8.8 times e to the negative 37. So yeah, that's pretty significant. That's a very, very small number. And then finally, we have the regression coefficients themselves here. So you can see we've got the y-intercept here, negative 69.16, and then the coefficient for each of the children, age, and BMI features. And then we also have our t-stat and p-values for each of these. The p-value is probably the one we're most interested in. So that tells us the significance level of that actual feature in the model. All right, so you can see BMI and age are well, below 1%. Children in the 1 to 5% range, so we would still consider that significant. Intercept also below 1%. So we've got ourselves a model with all significant features. All right, so let's take a look at the features real quickly so that we can see how they're distributed. And we'll just do that by creating a quick histogram. So you can see children, has a skewness issue to the right. Let's see about age. It's skewed to the right, not quite as dramatically, but it's certainly not a normal distribution. And BMI. A little bit better. That one's a little closer to normal, maybe slightly skewed right. And of course, we can take a look at charges as well. Yeah, we can see that those are definitely skewed to the right. So you can see charges has, all of them have, well, maybe except BMI, have some issues that we would want to address, but that's okay. We can run the regression without that. We'll get to addressing those later on in this module. All right. So now what can we do with this? Well, let's see if we can compare how our coefficients came out to a correlation matrix we might have made between these four features as well, these four attributes. So I'm going to go back to my data tab and bring up my data analysis add-in, go up to correlation, click OK. And I want the correlation to be, children, age, BMI, and charges. Labels are in the first row, and I'll set my output range down here to 027 rather than putting it in a new worksheet. I think I left myself enough room there, but I guess we'll find out in a minute. Yeah, so there's my correlation matrix. And what I'm most interested in is the correlation of these attributes, each attribute against charges. Okay, so as I like to do with my correlation matrix, I'm going to go ahead and color code it using conditional formatting. All right, so you can see for charges, children doesn't seem to be all that highly correlated, but BMI is moderately correlated, and age is certainly in the well into the moderately correlated range, and maybe even beyond that. All right. So let's see how those compare to the coefficients. So the coefficient, children was highest. Okay. Then came BMI, and then came age, which is the exact reverse order that we see here. So why would that be? Well, let's take a look over there. You can see children, we have 0s, 1s, 2s, 3s, a pretty small range of values there. So each tick in value means, a lot more change in that variable versus age, which has a range from 18, looks like as low as 18 all the way up into the 70s, and BMI, which has a range from 15.96 up to 52. So, 54 almost. So not quite the size of the range of age, but still, pretty much bigger range than children. So even though BMI has a smaller, so BMI with a smaller range of values, again, each tick means a little bit more variation in BMI than age does. So that's one consideration when it comes to deciphering these coefficients. What is the scale of each one? And there are ways to address differences in scale. We'll get into that in later in this module. So let's take a look at our R squared value again, 0.12. Well, here we've got the correlation of children, age, and BMI to charges. If we were to add them up, sum of correlations versus charges, well, we could just add them up here and say, well, look at that. That's 0.5634. Why not? Why is our R squared so low in comparison when we've got what looks like combining these three correlations, a pretty powerful combined correlation here? Well, each attribute, each feature individually is correlated against charges, but when you bring additional features in, some of those correlations overlap and explain the same variations. So the number of children may change and get bigger as you age. Your BMI may get larger as you age as well. I know it certainly has for me. So some of those correlations really are overlapping with each other, and the regression model, the multiple linear regression model, helps strip those overlapping effects away so that we're only considering each feature's true effect on the overall target value. All right. So let's keep that in mind, and let's go back. There are a couple other things that we can look at. These are measures that we can calculate to determine how well our model is doing. So the first one is mean absolute error. MAE. And the second one is root mean squared error. RMSE. All right, so to calculate those, we would need to know what the error is for each of our predictions. So how do we do that? Well, let's talk about how we can use our regression results here to predict a value. Let's say I wanted to predict insurance charges based on age. Okay, so age to charges. Well, my equation is my mx plus b slope equation that you would have for a bivariate analysis. Our coefficient is 239.9945, which is probably different than the coefficient you had for your bivariate analysis. So age plus charges, I'm going to take my, let's say we want to work with row 2. For row 2. So age to charges, I would calculate that as equals my coefficient times the age, 19, and then I would add my intercept. All right, so that gives me negative $2,356. So it's unlikely that the insurance company is going to have negative charges, so we would interpret that as just 0 charges. So of course, once we've built our multiple linear regression, a single variable doesn't really work for us. So what we want is age, children, or I guess children, age, and BMI. Versus charges. So to get there, we need to use the coefficient for all 3 and the intercept and multiply them by the actual values we get for our example. All right, so let's work through that. First thing I'm going to do is I'm going to copy children, age, and BMI and paste them up here where I'm working. So I'm going to do paste special, and I'm going to check transpose here, and I don't need the shading, so I'm just going to click values and click OK. All right, so now I've got my 3 coefficients, and this is for children, age, and BMI. Of course. All right, so now that I've got a row of coefficients and a row of feature values over here, I can use my sum product, which is a nice function I like in Excel. So it basically adds up the products of however many values I have in my row or column. So equals sum product. And then I'll take the children, age, and BMI over there. So you can see D2 through F2, and then comma, the next array, or basically range of data that I want, is my coefficients here, Q3 through S3. And then I can close my parentheses because I'm done with the sum product. But I still need to add my intercept, so that is this value down here, which is P21. All right. So now I've got a predicted charge of 6908.7775. How does that compare to our actual charges? 6908.775. Yeah, it's not great. We're off by about $10,000 there. So next, what we would do is go ahead and calculate the predicted charges for everyone. So we could take that same approach. I will do my sum product and my coefficients times my feature values, close my parentheses, and then add the intercept. All right. And I get my 6908.775. Now, before I copy this down, I need to check this. Okay, my feature values are going to go down with me, so having a relative reference is great there, but my coefficients and my intercept are fixed in place. So I want to make sure that I make those absolute, so I just click F4, and then F4. And now, whoops, didn't want to do that, did I? So I'll fix that. And now I've got my function. And when I click to the corner here, I can double click and it'll copy my function down as far as it sees data. All right. So that's my predicted value. So now take a look at both of these other measures we're looking at. Both of them rely on knowing what the error is that we encountered. So my predicted value, my actual charges, I can calculate my error by just subtracting my prediction from my charges, equals that minus this. So equals predicted minus charges. I can do the same thing again and copy that down so I can see everything. All right. So far, so good. And this one here, I've got a little message because I did not use charges and it's wondering if I wanted to. I'm going to ignore this error. Well, I'm not going to ignore it 1,300 times, but we can turn that error check off for this worksheet if we wanted to. All right. So now I've got the error. I can also calculate what the absolute error is. And that's going to be just the absolute value of the error. So you can see all it does is it flips the sign for me if it's negative. All right. That gives me the ability, and then I want to figure out what my squared error is. So I'm going to use that for RMSE. And that would be equals the error raised to the power of 2. So if I wanted to, I can then bring all these down to a more manageable level of decimals, just to make things a little easier on the eyes. All right. All right, so now I've got all the terms I need here. So the mean absolute error, well, that's pretty self-explanatory. I'm going to calculate the mean of those absolute error terms that I've got in column J. So equals average, and then remember that is Excel's function that calculates the mean. And I've got 90, 15, 44. So here, root mean squared error. All right, so I'm going to calculate the mean of the squared error in column K, so the same way, average, but then I'm going to take the square root of that. So equals square root. So that's the square root function in Excel. And then average, the square root of the average. Of my squared error. And then Excel had to fix my formula because I didn't enter all the parentheses at the end, but it gives me the correct result. Another way I could calculate this is I could actually do the average equals average of the squared error, close my parentheses, and then raise it to the power of 1/2. All right, once I fix that up, or I could, I guess, have done raise it to the power of 0.5. So either way, I get my 11,355. All right. So root mean squared error and mean absolute error are two other powerful methods for evaluating the performance of your regression model. R squared, we want to be larger, indicating better performance of our model. MAE, RMSE, we look for lower scores. All right. So hope that helps you, and we can figure out maybe how to move forward and do a little bit more with those categorical variables as we get back to the module.